This one, again, you want to invest the time to rewrite. So you see the subtraction in the numerator, so you want to break it up. So this is x squared over x minus 2 over x, and then this minus 4, and then this plus. Oh, and look at that negative exponent. I'm going to put it in the denominator. Okay, so I'll do one more little simplification. I'll rewrite this as x, and I'm going to take the time to put the 2 and then say 1 over x minus 4 plus 3, 1 over 1 plus x squared. What I meant to say, 1 plus x squared. Okay, so now let's take the antiderivative. So antiderivative means adding 1 to the exponent, so I'd get x squared over 2. This one here, you recognize it, that's ln, right? 2 ln of absolute value of x. What do we do with negative 4? So negative 4x, if you take the derivative of negative 4x, you get negative 4. And then I'm going to carry along this plus 3. And what's the antiderivative of this? Oh, you notice it. If I take the derivative of arctangent, I get that. And then I put a plus c there. Okay, so these are a little challenging. So what I'm going to do first is I'm going to plot these points. Don't always give points, but this one I do. So f of 0 is 0. F of 1 is 2. Make sure you leave lots of room between things. F of 2 is 0. And f of 3 is negative 2. So make sure you space them apart from each other. All right, so the next thing I'm going to do is this, the ups and downs. And I'm even going to draw it over to the side for a second. So this says that the graph is going up between negative infinity and 1. I'm just going to draw that going up. And then, a different color here, this says the graph is going down, I put the 1 there, is going down between 1 and 2, and then 2 to infinity. So that gives me the ups and downs, and let's put those onto the graph that we've got so far. So if I've got going up, and I know it has to go through that point, I'm going to have going up. And then I have going down between 1 and 2, and then after 2, it's going down again. So that puts those little tick marks over here. So that's the second thing I would do. So the third thing I would do is deal with what the slope is at the different points. F prime of 0 equals 3 means at x equals 0, the slope of the tangent line is 3. So slope equals 3. Okay, that kind of looks like that, doesn't it? All right, what's this next one saying? At 1, the slope of the tangent line is 0. Okay, for slope of the tangent line to be 0, it has to be a nice rounded top of a parabola kind of thing. All right, what's happening at x equal 2? Ooh, something bad. So when it doesn't exist, I'm going to put this one here, like I make a cusp or a vertical tangent. And notice I said that the function is continuous. We can't break it up. I want the function to be continuous. So I'm going to draw this vertical line. Could be a cusp, could be a vertical tangent. We'll see. And then the last one, f prime of 3, at that x value, the slope is negative 3. Hey, if I make a graph there, doesn't that look like a slope of negative 3 if I drew a tangent line? Okay, so I got the basic idea, as I'm just going to shift this down. So now here's where we do the enhancing your graph. So this says it's cupped up between negative infinity and 2. So I'm just going to draw it down here again. From negative infinity to 2, it's cupped up. So it's got to be up, 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 going through that point, right? And there's 1. And then it's still cupped up until 2, right? When it goes through the point there. So that's the shape of the graph. Whoops. Oh, I made a mistake. Sorry about that. Okay, so cupped up from negative infinity. Cupped down. Oh, goodness sakes. Cupped down from negative infinity to 2. So it goes like this, and there, is 2, and then it's still cupped down, right? Cupped down. Okay, so then what happens at this 2 point? So we've got this vertical line here, and then what do we see still happening? It's cupped up after 2. Okay, so let's put those pieces together. So I've got this 0.3 and -2, and there's the point. So it's cupped up and it's still going down. It can do that going down and still have a slope of -3. So there's my vertical tangent, right? And slope is 0, and that put all the pieces together. All right, so let's do this one here. So I'm giving you a new graph. Oops, it wasn't supposed to erase. Didn't think it would anyway. Okay, let's put that back in. Oh dear, come on. Put that back in and that back in. Okay. So if I'm looking at this graph and I was first to find the critical numbers, so the critical numbers, let's talk about the different kinds of critical numbers. So the critical numbers where the derivative equals 0 would give me -1 and 3. And so let's talk about the other kind of critical numbers where the derivative doesn't exist. Wait a minute. Can't you see that x equals 0? This doesn't exist. And I've neglected to say the function is continuous on all reals. So x equals 0 is included. So let's talk about what's happening between these critical numbers using the first derivative test. So first off, let's check out what's happening around the critical number -1, right? Before -1, the derivative is negative. After -1, the derivative is positive. So since y prime changes from negative to positive, f of -1 is a local minimum. It goes down and it comes up. Doesn't look like it. You're not looking at the graph to find the shape though, right? Okay, let's look at x equals 0. So we did x equal -1. Let's look at x equals 0. So x equals 0. What's happening here? Before x equals 0, the derivative is positive. After x equals 0, the derivative is negative. So at x equals 0, I see that y prime changes from positive to negative. So that must mean f of 0 is a local max. Okay, let's say last critical number is 3. What's happening? Before 3, it's negative. After 3, it's negative. So there's no extrema. I don't really need to say anything, but there's no extrema. This means extreme value, which means a local max or min at x equal 3.